try it out. Okay, no more orange packets. Put them away or I'm going to take them away. Oh.
That stuff is so good too. I have it. Yes, it's good.
I don't like vanilla.
Yeah.
Thank you. Okay, let's jump into it. So today, to kind of recap where we've been, so remember our unit right now is all about energy. Okay, so we started the first day and we learned about 9 different types of energy, from elastic to nuclear, kind of just what are the different types of energy. And we talked about this idea of energy flows, right? That it can start in one form and then be transferred to another form. We then spent a day talking about chemical potential energy, which is the energy that comes through the formation of chemical bonds, okay, classifying as endo or exothermic. Last time, we then talked about electrical energy, which also is linked to chemical because it comes from the chemicals, right? But the flow of the electrons, oxidation and reduction. Today, we're going to talk about 2 other types of energy. We're going to talk about nuclear and then thermal energy and how they're all connected. Wednesday, we'll kind of be putting it all together and be doing a similar thing that we did on the first day of flowing energy, but it's going to be now based on actual power plants. So in a power plant, no matter what form it is, can you track where the energy starts and then where it ends? And then our quiz for this unit is going to be on Friday. So just kind of heads up of like where we're at. Okay, also a reminder that this Friday is the deadline for retaking the stoichiometry quiz. So if you're wanting to correct and retake that, you have till this Friday to do so. Okay? And then after this unit, we'll, in a sense, take this knowledge into our last unit that we'll do for this term, which is our project unit about energy, wherein we'll obviously explain that more next week. Okay? So we're going to cover nuclear. We actually already did in Unit 2, so this is kind of a recap. Before I go to it for a smiley face, can someone by raise a hand, anyone remember the definition or the difference between fission and fusion? Go ahead, Caleb.
Fission is splitting atoms and fusion is combining.
Perfect, right? And we did a little thing with Play-Doh when we first learned about it. I had you make a model of like, this is what fusion is, this is what fission is, right? So I like the word fusion, right? Kind of makes sense by its name. Right, so fusion is when 2 or more nuclei come together. Fission is the process of when an atom splits. Okay, so add those definitions in. We're on page 10. Now, both processes have energy potential. Because of this idea of E equals mc squared, that there's energy contained within atoms, whether they split or when you fuse. While you're writing that, does anyone remember which one does harness more, though, fission or fusion? Sam?
Fusion does.
Fusion by a lot, right? So fission is still huge, right? Fission is like a nuclear bomb, right? Tons of energy within it. Fusion, though, is, technically they also have fusion bombs. They've never been used outside of just testing them, right? But fusion is like the power that's in the sun, right? Remember we dropped bombs on the state of Utah, right? The fusion bomb is the one that went from like Layton down to like Santaquin, right? But the fission one was still pretty drastic, but smaller in comparison, okay? Okay, does everyone have those definitions down? Okay, so with this idea, the energy that's coming from a nuclear process is known as the nuclear, it's because of the nuclear binding energy. This energy gets lost as those molecules form into new ones. Okay, so in a nuclear power plant, so if we're going to harness this energy for productive energy, right, there's nuclear power plants. They, as of right now, only work through fission. Scientists have not yet determined a way in which to harness the power of fusion on Earth. If you ever hear any headlines about cold fusion, that's what they're trying to accomplish. Is they're trying to accomplish using fusion because it has so much more energy, but as of right now, it's just through fission. So it's the same process in an atomic bomb where they take a large atom, they get that atom to split. In the process of splitting, the energy comes out. We then translate that energy into electrical energy, which we'll learn about next time, to then be used, and then obviously you end up with some radioactive waste in the end, which is sometimes the harder part of why people are against nuclear energy. All right, everyone okay there? Okay, so we mentioned this before once again when we learned about it. It's the idea of an unstable nucleus, okay? That an unstable nucleus is radioactive and undergoes radioactive decay, right? That's where it kicks out an alpha particle or beta particle and gamma particles, okay? But if it's unstable and we cause it to go through fission, then you get the massive amounts of energy out. And we'll look at that graph here in a second, and I'll have a question for you I want to work on with your table buddy here. Let's get some boogie boards. Okay, everybody ready? Okay, so what I want to do, I'm going to flip to the next page. The next slide is going to have a question for you. I'd like you to work on this as if there's 4 of you, divide into 2s, and each write your answer on the boogie board. If you're a threesome, you can all work together. Okay, and identify for me, this is a review question, will lithium undergo fission or fusion, and explain your answer. So put that on your board and to pick fission or fusion and explain why.
Plus an iron. That's just how I know.
Isn't there like a bar? Like
So this is kind of a recap
Yeah,
question.
it's
We actually
like the
had
most
this
stable.
on a quiz before, and I'm getting your brains to rethink.
Why is the Y? Like what's the Y?
Because it's only stable until, and when it's unstable, it needs to be.
Good, so I need to see fission or fusion on your board and why.
Wait.
When it gets too big, it needs to split into 2. And as you're going down, or like down through that table, it's gonna get bigger. So when it gets bigger, it needs to split into 2. And it becomes unstable.
Because that
And when it's unstable, then it's a split. Oh wait,
no, it's okay.
Thank you. Okay. Kira, will you guys read what you have on your board for us?
Yes, I said fusion. Iron is the most stable. Anything before iron will undergo fusion. Everything after will undergo fission to become stable.
Good remembering. So if you said something similar to Kira, that yep, it's going to do fusion because iron is that middle point. So good job, guys. It looked like everyone remembered that from our previous unit. So, okay, going on to the next category. So now thermal heat, or thermal energy, I should say. Okay, So keep in mind once again, heat is not just temperature. Okay, temperature is related to heat, but heat is a form of energy that's composed of other things as well. Okay, there's a whole study about heat known as thermodynamics. We could literally spend like an entire unit. In AP we spend a whole unit learning about thermodynamics. We're just briefly touching it here. Okay, what I want you to do though is get a highlighter out, and I want to highlight these key themes of what affects heat. Okay, so right here, everybody ready? Get a highlighter of your choice. Okay, the amount of thermal energy an object has is dependent on its temperature. So temperature is one piece, so highlight temperature. But it's also dependent on its mass, so how heavy it is or how much there is of it, and the types of atoms. So highlight those three things. So temperature, mass, and the types of atoms all influence something's thermal energy.
Wait, could you say that again?
Yep, so highlight temperature, mass, and the types of atoms. So those are the three things that contribute to something's thermal energy. Okay, everybody okay there? Okay, so on that note here, everybody, eyes up here, please. Focus back up front. Okay, so as we're talking about thermal energy, here's kind of an example to think about, right? That if I have 2 containers of water, okay, it's gonna take the bigger amount of water, it's gonna take longer for it to boil because there's more of it that I have to heat up. On that same note, on the reverse for cooling down, a smaller container is gonna cool down a lot faster than a larger container. So this is kind of what's bringing the idea of the mass plays a role as well, right? That mass also influences something thermal energy that it has. Okay? All right, so here's my question for you to put on your boogie board as a group. Ready? I'll give you 2 minutes to think about it. Which beaker, A, B, C, or D, has the least amount of thermal energy? Talk with your table buddy. You got 2 minutes. Put your answer on your board. Ready, go.
It's Steve's.
Okay, so talk as a table. Think about which one has the least. Okay, think about the 3 words we highlighted. Okay, and then put your letter on your board when you think you know what it is.
Because if there's a more amount, but there's less heat, it's gonna make it that much less. Have that much less, but
No.
I think, yeah.
Put it on your board once you have an answer.
far away.
Good job. I still have to retake the other test. Good.
I was talking, it's the same water temperature, just less of it. Less water. On the end, we're still like less.
But I think
It's gonna be easier to.
for the end, it has more sled, which makes it less.
But they're still the same temperature.
Yeah.
But that
The
one's
mass
less.
is greater on D, so it's gonna take longer for it to.
Oh, if you're trying to figure out the least amount of energy?
Yeah.
All right, 10 seconds and we'll show our answer. All right, in 5, 4, 3, 2, 1, show me your boogie board. Show me your board. degrees. Okay, so we're split between two of A or D. If you said A, have a smiley face.
I said A. Yeah, she said
Okay, eyes up here, everybody. Let's clarify it just to make sure we've got it. Eyes up here, everybody. Close your mouth. So, when we're looking at thermal energy, right, so the three things we said were temperature, mass, and the types of atoms. Now, in this case, it's all the same substance, and they weren't, that's a much harder question, and I'm not going to ask you that. Because if you start varying the type of substances you're looking at, like if one beaker's water, but one beaker's oil, like it gets much more complicated being able to figure out the difference. With them being the same substance, the more mass something has, and the higher the temperature, the more thermal energy it has as well. And so since we're looking for the one that is the least, we're looking for the least of mass and the lowest temperature. If it helps, if you're a mathematical person, the equation to calculate thermal energy, which we won't do in this class, but if it helps you in thinking about it, is you times the mass by the temperature. And so obviously, timing those together, in this case, we're looking for the smallest ratio. So, questions on identifying thermal energy in a substance or in a thing? Yeah, Jane. It's in the unit of a joule is what it ends up being in. So, because you actually also end up timesing it by this thing called the specific heat, which that takes into account the unique substance it is, because every substance has its own specific heat. So, yeah, good question.
In this example, would you just like multiply 5 by 5?
In a sense, yes. Like that's not the actual answer, but it could help you in comparing them. Like if you took temperature times that, you could, in a sense, see which one's the smallest. So, yeah, good question, Maddie. Okay, the next thing here, everybody, we're very chatty today. It must have been a popular weekend or something that happened, and everyone has to share. Right? No, I think everyone just has to either talk about the Super Bowl or Sweethearts, is what everyone's talking about, right? Okay, focus back up front. We got a little too much side talking going on. I want to have time at the end for you to work on your assignment, but we got to get through this first. Okay? Okay, with thermal energy, it's important to recognize because once again, it's different than temperature. So it is possible to have a beaker of water that I am heating up like it's on my stove, but it doesn't get any hotter. But heat is going in. So heat goes into the water, but the temperature doesn't actually go up. Does anybody know at what point that happens with a substance? Taylor?
When it's at the boiling point.
Yes. While water is boiling, it doesn't get any hotter. Have a smiley face, Taylor. In Utah, we boil water here at about 97-ish degrees because we're at a higher elevation. But let's just say for sea level sake where it boils at 100, right? That's when water boils at 100 degrees Celsius. While water is boiling, you can't go above 100 degrees. It just stays at 100 the whole time it's boiling. But does that mean the heat's not going in? Heat has to go in, right? If I turn off my stove, my water's going to stop boiling. So during a phase change, we see constant temperature. So notice this is temperature. So temperature stays constant during a phase change. Same thing happens while it's melting. While it's melting, it doesn't actually get any hotter. Once it's all melted, then the liquid can get hotter. What's going on at these flat plateaus is even though energy is going in, all of the energy is being used to break our intermolecular forces we learned about. We have to pull the molecules apart before they can start heating up again. So kind of, once again, that should hopefully help, once again, recognize the difference, that there's a difference between energy and temperature. They're linked, but they're not the same. Yeah, Jane?
Can water heat up more than temperature?
Not at a given pressure. The only way to get it above is to change the pressure. So that's actually how, does anyone have an Instapot or their mom has an Instapot? Or pressure cooker, that's how they work. Is they pressurize the system, which then allows it to boil at, I don't know how hot it goes, up to like 200 or more degrees. So that's why your food cooks faster. But, yep, not at, because pressure or boiling point is related directly to pressure. That's why actually if you climb Mount Everest, anybody, and wanted to cook some noodles, water boils on top of Mount Everest at like 70 degrees Celsius.
That's really hot.
But it's not hot, so it's actually not going to cook your food very well. It's just boiling at that temperature. Maybe I should get my vacuum. Maybe I'll do that again.
We should go up.
Yes. So like I can boil water in a vacuum chamber and stick my hand in it because it's cold.
Whoa.
But the pressure makes it just boil.
Have you done my experiment where you get like a trash bag and you put someone in it and you get a vacuum and then it sucks up?
No.
You should do that.
Let's find a way to fit that in.
It is so fun to do. It is scary. It's like you're like
Okay, our next vocabulary we're going to learn, everybody, is all about heat transfer. Okay? Now, as you're writing these definitions down, so there's 3 types of heat transfers. There's conduction, convection, and radiation. I'm going to go grab us something to use as we talk about this. Now, it's going to be very hard, I know for some of you. I'm going to put something on your desk. Don't touch it until I say go. No, don't touch it until I say go, okay? And I'll put it next to the most responsible person on this desk. Okay, write those definitions. I'm going to grab it from the lab.
I thought we were finishing our last.
That was what the time was
Oh.
at the beginning.
Yeah, it's in the
No, I didn't finish.
Wait, okay. Sorry, I keep asking this. So next time is the review. Okay, so I'll be here for that, and then I'll do some review. I have a competition.
exciting.
Yeah, it seems exciting. Just for dance. My senior year after. Don't touch.
I haven't checked their
It's gonna go right.
Oh, I know what this is, Jamie. You can trick me.
I'm not trying to trick you. I'm just putting it on touch it. Don't touch it.
Oh, I know what this is. It's the ice pack. You press a little bit and it goes and boil.
Oh, this is something.
Don't touch it.
I didn't know if I just did, so that's cool.
Don't touch it. Don't touch it. Okay, everybody ready? Do you have our definitions down? Okay, are you getting your definitions? Because I'm going to turn the slide. Okay, so conduction is the process of when heat moves from one object to another through direct touch. Okay, so here's your example of conduction. If you're holding a metal rod, that's hot because you're directly touching the metal, right? That's the heat transfer through conduction. Convection is heat that moves through a liquid or gas, causing warmer molecules to rise or cooler molecules to fall. So convection is like being heated through a fire because you're not directly touching it, but you're being heated through that transfer. And then radiation is heat that is moved at the speed of light from an electromagnetic light source. Can anyone think of an example of radiation? The sun. Yep. Yes, Kate? Do you have another example? Yeah, a microwave technically, you got heated through a microwave, or since your food gets heated through radiation. Yeah, good one. Have a smiley face, you too. Okay. And then, yes.
What's an oven? Isn't there like a convection onion? Oven? And so like, what's a normal oven? Is it radiation?
No, the idea of a convection of it is it just circulates it, so it like They all technically are, in terms of this definition, all of them are working through convection, but an actual convection oven just helps, rather than the heat just coming from like the top, it like circulates it around. Yeah, good question. That is kind of interesting, like scientific definition, it's a little confusing compared to like, because I would say another oven is still technically convection, because it's still just heating. But yeah, maybe we should sue the people who came up calling it a convection. That's not true. Yeah. Okay, are we ready? Okay, I'm taking that as a yes. All right, don't touch it yet, but you're about to. Here's my 2 questions, and then you'll get to do it. Okay? So what's going to happen is you, in a second, are going to activate the device. I guess that's what I'll call this. Okay, I'll tell you how to activate it. Okay? Once you activate it, I want you to identify 2 things, and you're going to write your answers on the boogie board. Okay? You're going to tell me number 1, is this classified as endo or exothermic? You need to explain your choice. Then, what type of heat transfer are you experiencing? So, convection, radiation, or what's the last one? Conduction. Okay? And then explain your choice. So, you should have 2 answers on your boogie board with an explanation. Everybody ready? Okay, so there's 1 device for every 2 people, so share it with your partner, or if you don't have a partner, you get your own. Okay? To activate it, there's a little metal piece in there. You're just gonna bend, right now it's like concaved. You're gonna bend it so it goes the other way and it should activate it. If it doesn't, call me over and I can help you. Okay, all right, you may now touch it. Watch it closely, it goes quick.
Oh, it's hot.
Did I do it?
It's hot. Feel it.
Oh, it's really
It's really hot. It's freezing. It's like freezing. It's like frozen though. What?
It feels so nice. Yeah, it's a heat warmer. Well, maybe these are like ice packs.
That feels like so good. How do you like that?
Okay, stop with your table, buddy. Write it on your board.
Yeah,
Okay. Classify as endo or
Endo.
endo.
And what type of heat transfer are you experiencing? Ready,
But
go.
it's hot.
Answers on your boogie board.
But it's frozen. No, but if it's hot, it's exiting.
It's just
It's not frozen.
But then the way that you get these back to liquid is that you boil them. Which is interesting.
Actually?
Yeah. We had like a bunch of these.
Like, that's so weird. Even if it's hot?
Oh, because I guess it like melts and stuff right here.
Yeah, because most of the time we had like this one that like it's like a shape of like a shoulder, so you put it on like your shoulders and like helps like relieve.
I need one of these.
Yeah. Okay, so you think endo?
Now, keep in mind with endo or exothermic, you're labeling the reaction that's going on in here. Is this reaction endo or exothermic? Think about the reaction. Don't think about your hands. Okay?
That's weird. So it's endo.
Don't think about your hands.
The metal thing, the reaction. It's the metal and something else is going in to cause the reaction. Right?
Wait, so what should I write?
So it's endo. So she was saying that don't think about your hands.
Yeah.
Just because you feel that it's hot doesn't mean it's releasing energy. Which means
So endo.
and then this would be conduction.
All right, 30 more seconds, and then this is going to be one where everybody shares. So someone from your table is going to have to share.
Would it be convection because it says it moves through a liquid, causing warmer molecules to rise?
It's not like
It says which did you experience?
You guys match up. The other people are matching up.
wait, why is it endo?
Because
Dude, that's nice.
the heat is going in.
forever until you boil it? That's amazing. Because this is still like so hot. I could like.
Okay, here's what we're gonna do. Ready? So every group, so that means either the two of you or your threesome. Okay, in a second, one person from your group is gonna stand up. Okay, and this time instead of sharing it out loud, I'm gonna tell you you're gonna go find somebody else in the room. I'll tell you like which way you're rotating. We're gonna do like the puzzle piece thing, and you're gonna see if yours lines up with theirs, and if it doesn't, try to convince everybody, and hopefully we all convince each other to the right direction and not the wrong direction. Okay? Okay, so between the two of you or the three of you, what you're gonna do is play 3 rounds of rock, paper, scissors.
No.
Ready,
I'm
go.
horrible at rock, paper, scissors. Okay, ready?
All three of us.
Rock, paper, scissors. Okay, yeah.
Oh, okay.
Yeah.
No! I am so scared.
Okay, are we ready?
Oh, I knew you were going to do wrong.
Stand up if you didn't win. Stand up. Stand up if you didn't win.
Just say that it's fine.
Like, he is
Just say that he is like reacting to something else, so it's not a product, even though it's warm.
Okay,
It's going into it.
so how we're gonna rotate, you ready? Listen to this, everybody. So back 3 tables, and it'll be a little off because of our threesomes, but it's fine if there's 2 of you. So back 3 tables, you're gonna come and talk to the front person. Front people go to the middle go to the back. Does that make sense? It's kind of circling this way. Okay, rotate. Say hello to your new friends. Say, this is what we thought. Is this what you think? And if they don't line up, see if you can get on the same page. Ready, go. So Kier, you'll come talk to Abby. Caleb, you talk to Maddie.
Oh, I see.
Does that make sense? There it is. So you go Sophia.
Hello.
Lisa, Abby. There we go.
Okay, we said it was EXO.
There we find the new. And then yeah, you can
connection
Caleb.
because I can only feel it by direct.
Yeah.
So
Yes. I think we said endo.
that's what I was saying, but my friend was saying EXO, so I just
Yeah.
Endo would be if he was going into it, so he
well, it's because it was cold and then it moved into like it spread and brought heat. Like it was entering.
I was thinking extra too, and she said like don't think about like your hands. And so that's why I was confused.
Yeah.
It's so much easier.
Yeah.
I feel like it is endo. That was my first initial instinct, but
Yeah.
just because it was like it went cold and you literally watched it.
Okay, you're gonna chance to explain.
Yeah. I don't know.
I'm gonna change it to endo.
I know.
Okay, so here's what I want you to do. Eyes on me real quick. So we all agreed, everybody said it was conduction, so we all understood that just fine, that it is the process of conduction because you're holding it directly. Where we're differencing is from whether it's exo or endo. So what I'd like you to do is head back to your normal spot, clear your board, and I just want you to put, do you think it's endo or exo? Ready, go. Rotate back.
Bye.
Put that down, and then we'll see how we're doing.
It's like hard now.
Okay, write it down really big. Do you think it's exo or endo?
I know.
I know, they're pretty addictive. My kids love them.
It's so cool. Hey guys, is it endo or exo?
What?
Is it endo or exo? Yes.
Okay. Okay, show me your board, everybody. Show me your board. Show me your board. Okay, we still don't agree.
Oh no.
Okay, we're gonna try one more time and see if you guys get there without me. I'll tell you, some of you are wrong, obviously, because it's only one of them. And some are saying endo and some are saying exo. Okay, we're gonna rotate again. This time, it should be, so this time, same person's gonna rotate, but we're gonna rotate in this direction. Okay? Well, either way, you're still like explaining it, right? I guess the other one could rotate.
Yeah, let's do that.
Okay, so this person rotates here, this person rotates there, and this person rotates here. Ready, set, go, rotate.
Let's rotate it. Okay.
And then Kate come here. Colin, come back there.
Wait, no, it's Kate's sister.
As long as one person moves. Okay, debate it. Debate it with each other. Get on the same page.
Something.
Bro,
Why would it be exo?
I don't know, but I was just saying stuff.
Yeah. Hey, this was like a circle. You know, like monsters versus aliens. Like, you know the movie Monsters versus Aliens? This is like the same color and texture. Bob, that was his name. That movie was so fire. Monsters vs. Aliens is the best movie of all time.
That movie was something.
And Bob just alien.
Oh, wait, this is actually trash.
Dude, in the main girl that's like a giant. Now I have a thing for like giants.
Bro,
Like goes over 20 feet.
I hope the audio for this off, bro.
They can't see my face.
Endo.
Shut up. I was looking back at the movie. The animation is like scary. It was so bad.
It's so
Like, no,
president. Bro, it's so bad.
no, they like did it so bad. It was like the worst mix between
It
like
worked.
trying to look good, but like it was like realistic only in the hair and like facial like wrinkles and stuff, but not realistic anywhere else. So it was
All right, do we agree?
what do you guys think of that?
Do you guys all agree?
Yeah.
All right, head back to your table.
Good discussion.
Yes.
Head back to the
Led
table.
by me.
Good job. And no.
Okay, are we ready for the table? We're just never gonna get there together.
We're gonna cause like World War III. Yeah, I know, for real.
Okay, everybody, eyes up here. Some of you are very stubborn in your ways. But I respect that. I respect it. That if you aren't convinced, not to just change because someone else is telling you to. But obviously, there is only one right answer. Pay attention here, everybody. Okay, eyes on me, mouth closed. Okay, so what I asked you to identify was the observation you saw. So the observation you saw was this before. You then flick the button, right? You saw it change, and you felt what? Heat. Where's the heat coming from? It's exiting this. No, it's not. No, it's not. How does it feel? Okay. What questions do we have for our endo people to clarify this? Because once again, I don't doubt that anyone who said endothermic doesn't understand the definition. But there's obviously somehow you're looking at this and you're not looking at it the right way to label it. Does anyone have a question they could ask
So,
to help me clarify it? Yeah, because otherwise, like, where's the heat coming from?
that's what I was saying. I was like, where's
That's what I'm saying.
like the little middle thing?
Yeah.
Nobody points fingers.
No.
Okay.
It was only like a group
I feel like we all give each other a hug.
Definitely.
It's okay, I still like you. Even though we have different opinions. Okay, now let's more exciting.
Like a
Okay,
horse in
fun
the, like,
fact,
the madness.
so I don't forget Caitlin's question. So by the way, everybody, in case you didn't know, so I heard some people talking about a phase change. The difference is, it's not exactly a phase change. It looks like a phase change in the sense it's going liquid to solid, but it's actually, what's going on here is this right here inside beforehand. So when it is liquidy, this liquid right here, how these work is it's known as a supersaturated solution, which means there is a ton of solid dissolved in the liquid. But it's almost more than what should exist. But you can force it there by boiling it. Then it's so unstable though that if you can convince just two of the molecules to start linking, you get the domino effect, and that's why it kind of like spreads out because they're dominoing onto each other and connecting back into solid form. In that process, they are forming bonds, and we talked about when you form bonds, it is exothermic. Now, these are called reusable hand warmers because to reset them, I just have to boil it away. So I just boil them back, they turn into this, and then you can use them over and over again. So, you want to pop another one? I know they're kind of addictive. They obviously aren't like as long lasting as like chemical hand warmers, like the ones that you shake. Those ones last longer. I think these ones are more dramatic, like the heat you feel is a lot hotter than those. But I think, I've never officially tested them, but I feel like they only hold heat for about an hour-ish, right? Where the other ones can last.
Oh, well, like after it gets reacted? Like,
Yeah, so once it's reacted, until it gets disturbed. So sometimes they'll accidentally just go somehow off, like when I pull it out next year. But otherwise, they'll just stay like this until it gets disrupted. So yeah.
What if you like go against ground?
Yeah, it can do it because like once again, they sometimes just go off by movement. Once again, that's kind of the plastic supposedly supposed to be thick enough to kind of help
Can we
prevent
test that?
that.
Can we just chuck whatever?
Okay.
Yeah.
And you can reuse them.
All right, our last topic today, everybody, is this term known as entropy. Okay? Entropy is an idea that everything moves towards chaos. So they are actually, there's a scientific measurement for chaos or disorder, and it's known as entropy. The idea is that just like heat, so the first law of thermodynamics says that energy cannot be created or destroyed, right? We know it flows, it changes, but energy doesn't come from nothing, and it can't just go away. The second law of thermodynamics says that the entropy of the universe is constantly increasing. The natural order of things is to get more chaotic. A simple analogy of this is your room, right? Or I like to use my desk. I start the day, every class period, and my desk is like nice and clean and organized. By the end of the day, it is not that way, and I have to do work to reset it. So we have to do work to overcome this natural order of entropy, because things, once again, just naturally tend to be more chaotic. With this idea of entropy, okay, does everyone have all their blanks there? Once again, entropy always goes up, and in order to decrease it, we have to put in work to make it happen. Okay, everybody wave your hand if you're not ready. Okay, so in these three, don't say it out loud, we'll call this, let's say, ABC. which one would you classify as having the most entropy? Put it on your board real quick. Which one has the most entropy?
Looks like A. Oh, okay.
It's gonna be like C.
C.
Okay. 5, 4, 3,
I just sent
2,
out
1. Show
like
me your board.
my
Show me your board.
and my dates because the school already posted them. Normally they like wait forever.
So entropy, once again, is about disorder and chaos, which C is more spread out.
What?
I knew it!
I was like, she's gonna say C.
Yeah.
Oh my gosh.
But like, that's not that.
Wow.
Okay, so here's your link here, everybody, with what we were talking about. Okay?
Because it's saying it's moving towards.
Yeah.
The type of energy
But that one looks like chaos.
with the most entropy, so all our types of energy, right? From elastic to gravitational, all our types of energy, thermal energy has the most entropy. Because of this, thermal energy is very difficult to make into something useful. So what happens is a lot of machines, from cars to power plants, refrigerators, they let off heat, and it's not used for any good. When we did our activity on day 1, thermal energy was one of the products a lot of things turned into, right? Even your cell phone, right? It heats up, but that energy just gets lost and increases the entropy of the universe. This is something that scientists, if we could find a way to harness or prevent the loss of thermal energy, things would be way more efficient than they are, because energy wouldn't just be lost and not be used for anything. Okay? So when something has high efficiency, it's giving off less heat. And so less entropy. Okay? All right, questions on entropy? All right, your homework assignment tonight, you can choose if you want to finish up your labs, you can. If not, you close your mouth to everybody. Your homework assignment tonight is just a short little Canvas quiz, kind of just reviewing what we talked about today. There's only about 8 questions, so it's pretty quick. So pull it out. If you're doing that, I will permit you to use your phone for that right now, or if you want to finish up your labs. But we have about 9 minutes till the bell, so let's get something done until then, okay? Ready, set, go. That's what I was saying. You didn't have to. Oh, that's right. So just do the bottom part.